Okay. Okay. Hello, everyone. I'm a lecturer in architecture at London South Bank University. My name is Daniel Tang. I'm also the author of this research. This is a project I've completed recently in MRAS architectural computation at UCL. The project title is An Investigation of Global and Local Visual Complexity and the Impact on Cognitive Load. From the background, this is an image representation of human visual process by an article in the scientific report. The global visual features refer to the state where the overall characteristic or attribute of an image can be perceived as a whole rather than focusing on the specific parts. The global features is referred to overall shape and form, and the local features are the details. In our visual processes, there are two major theories to explain how we recognize an object. First is the bottom-up process, which suggests we start with sensory input and then builds up a more complex cognitive process. This slide shows a neuroscientist David Marr's version, where we begin looking for the edges of the image, separated from the surroundings, and eventually builds up towards a more three-dimensional understanding before reaching the cognitive stage that associates the object with meaning. Please note that the edge detection stage is always considered to be the earlier starting process. The second theory is the top-down process, where it suggests the process is more interactive between stages. Context, expectation, and prior knowledge could look back and influence the earlier stage. This is a process that implies some subjective element of how we interpret visual content. So there are two competing theories to explain our visual processes. The research question is, first, to what extent does complexity of global visual features have a stronger impact on cognitive load? Suppose the complexity of global features is shown to be more impactful to cognitive load. The second question would be, could it mean that the cognitive load process also operates effectively in this early visual processing, which suggests an interactive top-down theory instead of a bottom-up theory? To answer this question, the key is to measure the status of cognitive load and determine if it is a global visual features affecting it by measuring the disruption of our time perception. The methodology has been proven that for decades, visual capacity, level of cognitive load, and accuracy of time perception have a causal relation. Higher visual complexity would lead to a high cognitive load. When cognitive load is high, it disrupts our ability to estimate the duration of time. By recording how time estimation was disrupted by participants when they viewed the image with different complexity, in this way, we could work out the statistical inclination between visual complexity and cognitive load. Typical retrospective time estimation is an experiment. We ask participants not to actively measure the time in their mind and even unaware of the experiment intention. In this scenario, they rely on the memory to estimate the duration of time. Usually, they tend to underestimate the duration in this setting. The key is whether the underestimation rate would be influenced by the visual complexity. We expected a more complex image would cause a high cognitive load to result in less time underestimation. That is, time runs slightly longer compared to a lower visual complexity in the perception, simply because a more complex image would have more information for our memory to reconstruct the time. The next important component of the experiment is to measure global visual features in complexity. Port segmentation is an algorithm that merges nearby areas with similar colors and looks for the edges. A stronger segmentation level will result in greater simplification. This segmentation is used to simulate the image global feature because it is very close to how our early edge detection process operates. This is an example of a different level of approximation, which we call the granularity coefficient. The greater the value, the stronger the image simplification. And the file size is used to gauge the objective visual complexity of the image. The different file sizes of these building images at various approximated levels are also used to calculate correlation with the time estimation result. If the results correlate better at a specific segmentation level, it means we are not likely processing the image at that simplification level in our connection. The assumption is that the more complex global visual features will have less time estimation and less time underestimation. Sorry, I mixed up the page. We'll have less time underestimation. If the global feature more influence participants, if a specific granularity coefficient image correlates better with the time estimation result, that implies image simplification at that level matches what we are actually looking at. The experiment, we invited 36 participants to view PowerPoint slide with 60 images on an LCD screen. The set of photos has a sort of range of JPEG file sizes. Each image is programmed to be shown in varying duration, from 18 seconds to 34 seconds. The participant had to estimate the duration of each image after it disappeared. This experiment tests how much participants underestimate the duration of image with different complexity. We measure cognitive load by utilizing how visual complexity influences our time perception. In retrospective timing, participants tend to underestimate the duration, but more complicated visual stimuli would increase cognitive load and affect how we remember the passage of time, leading to less underestimation. A total of 60 images were used, including 6 abstract images and 5 natural images, were included and shuffled with the built environment images to reduce participants' expectation of what they would see next. These are the example of the building images out of the 48 building images. There is 2 methods of collecting the data. First is recording by the eye tracking position. Second is the questionnaire for participants to fill in during the experiment. The eye tracking device provides gaze speed and where they were looking at in the recording. Then the questionnaire from them to report the retrospective time estimation and how they judge the complexity of each image. Finally, familiarity and pleasantness are bias factors in case they also have an effect on the results. During the experiment, participants were only able to see the image. The movement of the web pad is hidden from their screen. The screen video recording of the experiment is then used to calculate the gaze speed and where they were looking. This is a visualized version of how participants look at the image. The temperature map on the image edges shows how long and how often the participants were looking at the global edges of the images. So this is a representation of what's behind the scene. The color map represents the duration and the occurrence of the view actually intersect with the edges of the images. But what they were seeing is the original image without this segmentation. And the counter on the top right is just showing the number of occurrence. And we use this data to revert and calculate the gaze speed. As the result, the experiment result shows that the longer the participants looked at the edges, the slower the gaze speed were, which is a sign of high cognitive load. The bias factors, familiarity and pleasantness, were insignificant to the complexity rating and retrospective timing estimation result in this setting. The first finding, we support the time estimation result that the more they look at the edges, the higher the cognitive load. This shows the participant ignore the finer details during the duration of the image of the experiment. In some research, they found that bias factors have effect on time perception, but in this case, it is less significant. Another finding is the effect of objective image complexity, in this case is the file size, only indirectly affect retrospective time estimation. This means that how subjectively the participant feel the image complexity has a more direct effect on time estimation than objective complexity. The objective complexity, which is referring to the file size, has a quantifiable value for the image complexity. Although objective complexity still affects how we judge image complexity subjectively, it shows that visual complexity inherently is interpretive and hard to quantify objectively. Another result is that the overall results show that the participant tends to underestimate the image duration. And the complexity rating, in this case is a subjective rating, correlates positively and significantly with time estimation in a statistical term. The more complex image result is less time underestimation. This matches with expectation, although retrospective timing can result in time feeling faster retrospectively, the high quantity load would make time feel relatively slower. Back to the research question, to what extent does the complexity of global visual features have a strong impact on cognitive load? After further analysis, this is a correlation coefficient comparing the complexity weighting from participant with the image or in different level of segmentation. Results show segmentation at 0.025 granularity coefficient correlate best with the time estimation result. And this is the graph representation of the data. The regression analysis showed that across the 7 post-segmentation granularity coefficient values, the 0.25 is the set of images file sizes that correlate best with our participant complexity weighting. This means image segmentation at this level has the highest impact on cognitive load. This is because the increase in image complexity at this level of segmentation correlate best with the complexity rating, which directly impact time estimation. For the conclusion on the first question, the correlation is stronger with the complexity rating and time estimation when image file size is at 0.025, suggesting a plausible theory that complexity is rated on how an image truly impacts us in the earlier cognitive stage. We may look at seemingly visually complex image with intricate details, but what truly impacts our cognition is the global feature of form and shapes. Since the subjective complexity rating has a direct impact on time estimation result under ANOVA and regression analysis, the granularity coefficient at 0.025 has a most indirect effect on cognitive load. The left image is the participants normally see in the experiment, and the right is the version and the level of simplification that actually have impact in the time disruption, which is representing the cognitive load in this setting. And here's another example showing what they were looking at in the experiment and the level of complexity that has impact on the connection. Finally, there is a second question to answer. Suppose the complexity of global feature is shown to be more impactful to cognitive load. Could it mean that the cognitive load process also operates effectively in this early visual processing, which suggests an interactive top-down theory instead of a bottom-up theory? The conclusion for this question is, as the experiment results demonstrate, the complexity of global edges has a strong effect on cognitive load. Since we have established that edge detection happens at the earlier stage, and cognitive load, which operates at a later semantic stage, where time perception is being disrupted, the bottom-up theory is rendered implausible. leaving the top-down interactive account of the visual process a more appropriate theory to explain the experiment result. It means that as early stage have effect on the later quantitative stage, top-down theory would be able to better explain this phenomenon from the experiment. I consider this project has potential to explore further by testing out disruption in time perception in a closer to real-life environment, where three-dimensionality, body movement, and affordance can also involved. I'm looking forward to advance this research in this direction at the near future. Thank you, everyone.